Tonight we're trying to show that there are no positive integer solutions. Now, just by example, let's look at ordered pairs that are not a member of n cross n. Let's say 0, 3. I'll make up some others here. -2, -8. These two ordered pairs are examples of ordered pairs that are not a member of n cross n. N cross n means the positive integers, all positive ordered pairs of positive integers. So we're not looking for the presence of a single zero invalidates the solution as far as this problem goes. So we want to show that there are no positive ordered pair solutions to this equation. Now, there's a cool little trick here. It's pretty famous in math competitions. It's sometimes called Simon's favorite factoring trick or something like that. And SFFT, yeah, Simon's favorite factoring trick. Michael Penn calls it complete the square, or complete the product, excuse me, complete the product. But what we do right here, we actually create a binomial factor out of thin air. What we did right here, first step here is just we chose to factor an x out of this term and this term to get to this piece right here. Okay, that's all we did. Nothing happened there. And then we noticed that 1 plus y is a binomial factor. And we can create another binomial factor called y plus 1 right down here by adding 1 to both sides. You see how we have 478, now we have 479. Okay, and also once we do that, you see we have 1 plus y as the greatest common factor, if you want to call it that. And this bothers, this is slightly, it takes a little bit of practice to get used to this, but if you envision a 1 in front of this, a 1, that's exactly the one that you see right here. This one and this one are the same thing. Okay, so out of thin air, by this tiny adjustment, we have a pair of binomial factors in two different variables, and we can equate it to 479. Now, the approach here is two obvious factors of any integer or one in the integer itself. So we can write this as 1 times 479. Okay, like that. Now, the approach here would be just to equate both of these factors to each of these factor pairs, if you want to call them it. So in other words, we could write down 1 plus y equals to 1. All right, which clearly 0 is the solution to this, which would invalidate the solution. Now, x plus y, we could stop right now, but we'll go ahead and write down x plus 1 just to make sure I'm getting the point across. See, just due to this factorization of 479, we've gotten this far, so we would get y equals 0. And then x equals to 478, right? But notice that's not a solution. It is a solution in the integers. There's no doubt about it. This is a solution to this equation in the integers. You can verify it if you want. It's definitely a solution in the integers. You can see trivially up here that it all works out. X would be 478. The rest of the stuff would be 0, right? So, so it is a solution, but it's not a solution in the positive integers, all right? And also, you could reverse things, all right? You could reverse, and it would just be the same kind of thing, except you would have y is equal to 478 and x equal to 0, right? Now, you're thinking, okay, fine, these aren't solutions, but the kicker right here, we're virtually done right now once we observe that 479 is prime. Now, that's not an easy observation. You don't just know that, but 47 is prime, which means this is the only possible factorization. So any work that would be done in this problem really is more based on establishing that 479 is a prime number. And notice that 479, the square root of 479, this is a famous test, the way you test for primes. 479, the square root of 479 is less than, what do we need here? 22 squared? 22 squared square root, right? Which is equal to 22. 22 times 22 is 484, I think. Okay, so we got this. Now, So all we really would have to check would be all the primes less than 22, and that would be 19. This is a basic number theory result. Check all the, if it doesn't have any prime divisors less than the square root of the integer, then it's going to be prime. All right, and so let's see what else. 13, 11. Now you would have to check all these by hand, which isn't hard, but I'm not going to do it here in this video. 7, 5, 3, and 2. Aren't these? I think I've listed all the primes less than 22. All right. And so you'd have to check all these, but it's not too much trouble to check this for 479. But none of these primes divides 479. Hence, it's a prime number by the result I just stated about if you take the square root of an integer and then check all the prime divisors less than the square root of that integer. If none of those prime divisors are divisors of the original number, then the number itself is prime, okay? And that would be the case if you went to the trouble to check 19, 17, 13, 11, 5, 3, and 2. So again, I'm not going to do that, but 479 is indeed prime. You can verify that if you want. And so we've shown there's no solutions, okay? We verified this would be the only attempt, and then the reverse of this would be true if you just reversed the numbers right. And so you would always have 0 as part of the solution. All right, so again, this is an integer solution, a valid integer solution. In fact, it would be the only integer solution at all for this thing. So we are done with the problem, folks, right here. Because of this 0 right here, we struck out finding solutions to this equation. Now, you guys may be familiar with the shape of this equation. This is a hyperbola. And so what we've just shown is that for this hyperbola, there is no positive natural number lattice points. And in fact, there's just 2 lattice points, period. One would be 0, 478, and the other would be 478, 0. So anyway, that's of interest to some people. A lattice point is just an ordered pair that's comprised of integers. Okay, finished. Good night.